Hello, welcome to Sunday Science Q&A. We're back. I was going to say we took a week off. We didn't take a week off. We were doing the Cheltenham Science Festival last Sunday. We did an early evening show with Grace Petrie and George Egg and Katie Mack and Josie Long, and that is still up online, as is our Sea Shambles that we did in replacement to us being at the Albert Hall. We did it all in our lofts, attics, or if you're Steve Backshall, what appeared to be a luxury houseboat near some mallards. Thanks very much for joining us again. We've had loads of questions. We will try and deal with as many of them as possible. If you also have questions during the show, if you send that to the live feed, we will try and deal with those as well. We have a brilliant panel. I'll just go through the tedious little bits and pieces, which is one, there is a tip jar somewhere on your screen. If you're able to, no problem if you're not. It is free to everyone. But if you're able to tip, that all goes towards various different funding of art centres and artists during this weird time where basically each new month you cross out a new month of your diary. I'm crossing out November at the moment. That was a waste of money. It's a great big desk diary, $11.99, lovely Edward Hopper paintings. I'm not looking at any of it nowadays. Also, we've got a new episode of the European Space Agency series, which Helen was a major part of, really. And we're going to be meeting Helen Czerski again, as usual, in a moment. On Thursday evening, we're doing the third part of the I'm a Joke and So Are You kind of conversation and stand-up and poetry and nonsense. And I've also got a guest, Josh Cohen, who is a fantastic therapist who I interviewed for the book and also a very good author as well, who's been on book Shambles in the past. And we're going to be talking about some of the kind of mental health and therapy issues that I discussed in the book, going off in other directions there. So that's Thursday night. And Helen's new BBC show, Ocean Autopsy, is on iPlayer at the moment. And I will also mention at some point Simon Singh, who's one of our guests. Simon has his parallel maths project up, which is weekly maths puzzles, approximately for 11 to 15-year-olds, and you can sign up at parallel.org.uk. I will mention that again before the end. So first of all, let's meet, every Sunday, Helen Czerski. Helen, how are you?
I'm doing very well. It's sunny.
It's interesting. We did a show about that on Monkey Cage the other day. Sun, good or bad? We came up with good in the end. It was decided, and it was, who did we have on that? It's not gone out yet. We had Steve Jones and Lucy Green and someone else. I've totally forgotten. Oh, Tim Minchin. I've totally forgotten Tim Minchin there. Yeah, Tim was there.
Well, his hair looks a bit like the sun. You know those things where you have the eclipse and you can see all those tendrils coming out. I think I can see him in that role.
He wasn't. You see, the trouble is that because of the time difference with him being in Sydney, he was in a very dark room drinking some form, I think, of Merlot. So we were getting a very different kind of mood from him than from the rest of the panellists. Now, I should find out straight away. You have a show and tell for us. What is the show and tell today?
I do. I have some. I have this, which I'm going to hold up. There we go. So this is a piece of malachite, and it's a copper ore. And the reason I'm showing it to you is that I have. When I was a kid, I was fascinated by gemstones, and you know, it was the thing you found in gift shops of various types. And my parents used to have to pull me away because I'd be like rifling through looking for the prettiest one. And I would have loved this as a kid. So this is one of the earliest ores of copper, and it was also used as a green pigment. It's not used as copper ore anymore. But I just really like it because it's one of the things about rocks and geologists, when you study geology, which I did for a bit as an undergraduate, they tell you about all the colours of rocks. Never really that colour. They're all sort of shades of brown, and you have to kind of get yourself inside the geologist's head to be convinced it really is a colour. Anyway, malachite is definitely a colour, and instead of the sort of coppery, orangey sheen of copper, it's this beautiful green. And I've got this because it used to be like 4,000 years ago, people were mining this stuff from the north of Wales, and there's also malachite ores in Cornwall, and this is where copper came from. But the amazing thing about it is that to get copper out of this, you have to basically heat it up until it stops being green, which sounds so boring. I can't imagine the person who put this beautiful green rock on a fire, and then you have to do something else to it, then eventually you get copper out the other end. Anyway, so that's my show and tell. I just think it's really pretty, and I think there should be more malachite in everyone's lives.
That was beautiful. That was just on the cusp of you turning into Percy from Blackadder 2 at one point there, which was highly enjoyable.
It's green.
We are also joined by, I'm going to go to Monica next. Monica Grady, who I think the first time she was on Monkey Cage was with Patrick Stewart. Am I right in Stewart? Am I right in Patrick Stewart the first time, Monica?
It was Patrick Stuart, yes, indeed. Captain Picard himself.
Now, this is the reason I wanted to go next to you was just because of looking at that malachite,
Oh.
and it's something. Hopefully, I don't know if you is the signal not great. I'll tell you what. We might come back to you, Monica, if the signal's not that good. I'm going to go up to Simon, but get ready for questions about meteorites, if you can hear that. Simon, it's lovely to see you. We've had a vote, and everyone's decided that it is the best backdrop that anyone's had yet.
Courtesy of one of my sons who's loaned me his bedroom, yes.
Now, is that stenciled by you or another member of the family? Oh, it's going very well today. You're entirely on mute now. This is what I like about doing science shows, is finding out whether the technology works. Helen, you might have a lot of questions to answer today.
Simon made a great face, though. I mean, the moment when you suggested he might be on mute, and it froze for a second in that face. That's what
all artistic credit goes to Mrs. Singh. Yes, nothing to do with me.
So you've got a show and tell for us today. What have you got?
Yeah, so I'm just seeing rocks, and I'm wondering whether rocks is going to be a bit of a theme. I wish I brought up a belemnite. I found a belemnite the other day, which is one of those old fossilized squids. And the reason I wanted to show it was to ask whether, I think Mary Anning's assistant down in Lyme Regis used to grind up the inside of belemnites, and you could somehow still extract the ink. And she used to use the ink from fossilized belemnites to illustrate some of the findings of Mary Anning. And that all sounded too good to be true. So if anybody knows if it is true, I'd really appreciate that. But
that is such a beautiful idea, though. The idea of looking at that all the different sense of life that has gone into then creating. Oh, that's fantastic. If it's true. We've decided it's true.
Yeah. So if it's not
science allows that. Science says if it's a nice story, you're allowed to. Isn't that how science works? I think that's how science works.
Shall I keep quiet at this point?
Yeah, you keep quiet with your science communication hat on. Remove that for the mystical hat.
But the thing I found, I hope you can read it. It's a homeopathic remedy, and the writing might be reversed and may be hard to read it, but it's actually a homeopathic preparation of Berlin Wall by Ainsworth pharmacists. And the whole thing about homeopathic Berlin Wall is it's used for treating isolation. So I've been taking regular doses of this over the last month to help me get through those tough times.
Where did you get it from?
Well, Ainsworth Pharmacy, apparently. One of the homeopathic pharmacies here in the UK. 35 New Cavendish Street. So yes,
working. It means you should have a persistent hankering to read John le Carré novels. Is that happening?
Not yet. No, I don't read novels.
Oh, of course you don't. Some made up old nonsense. I just because you mentioned homeopathy, I was interested where thinking of your book that you wrote with Edzard Ernst, the Trickle Treatment. Something that I don't know what your take. 10 years, 12 years ago, when we started doing shows together, a lot of what might be considered some of the kind of charlatan debates and some of the quite dogmatic debates, and sometimes that will be involving creationism, sometimes involving alternative medicine. It feels now like a lot of that style of debating, which seemed very much to be in the kind of pseudoscience area, seems to be almost mainstream now, not just in that area, across the board, in terms of the way we see so many columnists, we see so many political ideas being argued in such a dogmatic way. Do you think there has been a change in this kind of, there's a certain form of kind of paranoid diatribes, I think, which reminds me of the kind of conversations we used to talk about, skeptics in the pub and stuff like that?
So has that moved? Has that tone infected all sorts of other areas of discussion? I guess it has. I mean, we now have topics that polarize people from how we deal with COVID to how we deal with Brexit and everything else. So maybe I think it's just the same for any heated. Any highly controversial topic where people are divided, and that certainly happened with homeopathy. If you're an ardent supporter of homeopathy, if you genuinely believe that it works, if you genuinely believe that as a homeopath you are helping people, then you would see me as being the enemy. I'm trying to stop this natural, safe mode of healing from reaching people who desperately need it. And so I quite understand why homeopaths are incredibly passionate about it, and sometimes they got quite personal about it. And similarly, as scientists or rationalists, it's understandable that we got quite strident in some of our opinions about the money that was being wasted and the lives that were being put at risk. So yeah, I think that certainly was the tone of much of the debate. Nowadays, I think there's much more questioning of homeopathy. So, stand-up comics and people writing opinion pieces tend to be, the assumption tends to be that homeopathy is dodgy. And certainly in the last 10 years, we've seen people like the NHS really clamp down on homeopathic spending. And that's been really important, because in the past, homeopaths would always say homeopathy must work because the NHS funds it. Well, that's no longer really true. So I think the tide is turning in our favour in that particular debate.
So that's good. So the tide's turning in your favour there. It's just going against us in everything else. That's fine. I mean, that was a very balanced answer, by the way. So that's not going to trend on Twitter. Monica, hopefully you can hear me now. How is? Can you hear me, Monica?
I can hear you. Can you hear me?
Yes, it's a slightly bad connection, so I apologise, everyone.
Hello?
Always a bit of a debate on this. I will. Let's see if we've got any more. We might have to drop Monica out and reconnect, and we will come back to you. If I think that might be the best thing, because I think otherwise we're going to constantly be going back to hello. Yes, this is
Hello.
Rochdale 213.
Hello. Hello.
I think we're going to try that connection again, Monica. We're going to drop that out, and we're going to try and reconnect.
All right. Okay. Bye.
We will hopefully, Monica. This is one of the most enigmatic performances we've had from any scientist, so that's very exciting. I'm going to start off with you, Simon, because, of course, you wrote a tremendously successful book, Fermat's Last Theorem, which also a documentary as well. And the first question we've got, I apologise for the way not all of these have names attached to them. Not everyone left the name of these questions. What do you think the next Fermat's Last Theorem might be, or perhaps what do you hope it might be? Some long unsolved puzzle of maths.
Yeah. I mean, the great thing about Fermat's Last Theorem was that it was a long unsolved puzzle, but it was also comprehensible. It was something that you could explain to a teenager. In fact, Andrew Wiles, who went on to prove it, came across it when he was a 10-year-old. So I think the beauty of Fermat's Last Theorem was this unsolved problem that everybody could understand with a bit of elementary maths. The challenge was, how do you solve it?
Hello?
Hi, that's great, Monica. That sounds good.
Right. I'm now on my iPad rather than my computer. Is that any better?
That's sounding better.
Brilliant. We'll give that a go, Monica. We'll come right back to you. We're just going to talk quickly about Fermat's Last Theorem, and then we'll be talking this is the most chaotic one we've had. We've had some very professional ones, and Trent's been not a good week with technology. Not a good week with technology. Well, right. So yes, Monica, we'll be back with you in a moment. So Simon, Fermat's Last Theorem.
Yeah. So the problem that springs to mind that's like Fermat's Last Theorem, but it's already been solved, but I'll give it a quick mention, is the 4-color map theorem, which is if you have a map and you want no two regions to have the same color, how many colors do you need? And this goes back to the 1800s. I think it was somebody at UCL posed it, and people thought about it for a long time. And you couldn't find a map that needed 5 colors. Nobody could find that 5-color map, but nobody could prove that 4 colors sufficed. And that was eventually proven in the 80s. And again, that's a problem with a simple pen and paper and a little bit of sketching. You can explain that to a kid. Proving it, again, turned out to be a horribly big problem. But if we look at outstanding problems today, the Clay Mathematical Institute, or the Clay Foundation in America, in the year 2000, named the 7 big problems that they felt were the outstanding pinnacles that mathematicians should be trying to climb. And of those 7 problems, one of them has been proven already, the Poincare conjecture, which is all about kind of spheres in higher dimension and how you define them. And that was proven by a guy called Gregory Perelman in Russia. And you got $1 million if you prove that, but Gregory turned down the money because he just said, I do this stuff because I love it and I don't need the £1 million. of the remaining 6 questions, which cover things like actually theoretical physics, fluid dynamics, all sorts of the Hodge conjecture and various things. The one that's maybe most comprehensible, although I've tried to explain it before and I've got it wrong, is P versus NP. So this is the idea that there are some problems in math that are kind of doable. Given the size of the problem, a computer could eventually crunch through it and solve that problem. And they're called P-type problems. And then there are other problems which are apparently fundamentally much harder. And they're called NP-type problems, non-deterministic polynomial, I think. And the question is P-type fundamentally different from NP? Are the easy ones fundamentally different from the hard ones? Or have we not yet figured out the way to make the hard ones easy? And that's an outstanding problem. If it turns out that we can make the difficult ones easy, then suddenly a whole load of things we'd love to do, we know we could do them if we were smart enough, as opposed to them always being intractably difficult. So I think P versus NP is out there as a long-standing problem that mathematicians would love to know the answer to.
Oh, wouldn't it be nice if someone before the end of the show gives us a solution? So there's a little bit of pressure for you there now. Monica, hopefully we can hear you now and you can hear us.
I've got a meteorite.
Right. Let's see. So lots of questions about meteorite. We can hear you. I'm just going to give you, there's about a 3-second delay. So please, when you hear this, tell us about the meteorite. Right.
Well, first of all, it's a bit of stone and it's got stone and it looks as if it's burnt on the outside. So it's come from the asteroid belt, 4,767 million years old, older than any rocks on the Earth. Originally, of NP problems, but that sounds more like a semiconductor than anything else. But there's my meteorite. How's that?
That's great. I'm going to give you the first meteorite question. We have a few. This is from Jay, who is aged 8.
Right, go on.
And Jay would like to know, what's the oldest meteorite that's been discovered on Earth, and where was it discovered, and where did it come from?
Right, Jeff. All meteorites, more or less, have the same age, 4.7 million years. So all the ones that come from the asteroid belt have minus, a few weeks or a few years. So it's very difficult to say this particular meteorite is older than that particular one, because the big groups of meteorites all have the same ages. The ones that have different ages come from the moon, and the ones that come from Mars are so young that they're the same age as they formed on Mars at the same time the diamond walking on the surface. And some of those have been found in India, in Africa, in America. All over the place.
Now, we're going to have slight pauses because we're getting you 3 seconds late. I'm not sure quite how your delay. So that's why if you think that we're furious with your answer or what, it's not that. It's just going to be a little. So I'm going to stay with you while we've got you, just because there's a few more questions. And this is one from Liz who says, it's something we've talked about before. How much does the universe change for you when you actually touch pieces of rock that have come from somewhere beyond Earth?
How much does the universe change for me when I look at a rock from beyond?
I mean, what we talked about before.
Well,
sorry.
What I was going, it makes me realise that just getting rocks doesn't answer all the questions that we have, because so much of the Earth is hidden So we can't get at the core of the Earth, and we can't really get very, very deep down into the crust of the Earth. Different types of meteorites. We can see the iron meteorites that come from the cores of asteroids, and we see stony meteorites that come from the. Hang on a minute. I'm happy to hold up the sign.
No.
All right.
Right.
Forget that. So.
Right, what we're going to do is what we might do is we might try you on audio. Trent's going to have a little bit of a conversation with you, Monica, because we may well just try you on audio. It might be by the way, before the end of this episode, we will tell you who Monica's Wi-Fi provider is, and then you can make sure you don't use them either. So we're going to come back to Monica in a moment. I apologise to everyone for the fact that this is every now and again. Of course, this is always one of the risks. Is sometimes on some days just the Wi-Fi is not as good for some people. This is a question, Helen, which I think almost comes off the back of the question I asked Simon. And this one, Lucy would like to know what area of physics is the one that you are most hopeful there will be a solution for within your lifetime. So that gives you.
So there's a thing here, which is that the question is, are the solvable bits of physics the most interesting bits of physics? It is very similar to what Simon was saying. There was so solving is a strong word, but understanding better, we can sort of deal with that. And there is one area of science which is really complicated, and it's funny that it's complicated because we can all actually see it, and that's turbulence. So turbulence is when you have a flow of a fluid. So it might be, wind carrying particles. It might be when you breathe out. It tends to be a kind of fluid flow. So that's either a gas or a liquid moving around where everything's kind of mixing up. So it's like, when you sort of stir tea and you see swirls, but then the swirls are complicated. The inside of a washing machine, basically, that's the kind of thing to imagine. So turbulence is really important in the world because basically it mixes things. So whenever we have, wind blowing along flat, for example, we think of the wind moving horizontally, but actually it's kind of mixing in where there's a boundary layer where it moves over the bumpy surface of the earth. It's getting sort of bounced up, and then you get these swirls, and that mixes in the layers of the atmosphere. And there's lots and lots of applications where turbulence is important for mixing. And actually, coronavirus is one of them. If you want to understand, people are talking about droplets that people might exhale, which may or may not have a virus particles on them. If you want to understand where they go, that is a turbulent flow problem. It's not like they come out and just sit there. They move around in the flow. And so we do understand turbulence to some extent statistically, but I think there are a lot of questions in turbulent flow that are really hard to answer. And we can do a sort of decent job with some numerical modelling, but it's complicated every time. And it would be nice if it wasn't complicated every single time, if there was some kind of bigger explanation which got you through more of these problems. So yeah, it's not a single answer to a single problem, but I think the most practical and useful questions are the ones that don't have nice clean answers. They're the ones the pure mathematicians don't like them. The applied mathematicians are all over them. So I would pick turbulence as the thing that if we could understand and predict it certainly more easily and with less computational power, it would let us understand a whole load of other things a lot better.
Brilliant. Thank you, Helen. Simon, this is from Prandit, who says, I half remember, I always like these ones, I half remember seeing a science video about quantum coin flipping. I can't remember what it was. I just remember the phrase, and it's always stuck with me because it sounds very cool. I'm hoping someone who wrote the code book can explain it so even I can understand it. Your minute starts now.
Right. So the only bit of the code book that involved quantum was something called quantum cryptography. So there's this idea that we live in a golden age of cryptography. If I want to send you an encrypted message, we can download some free software. I can email you something, and all the world's computers working for a billion years would not be able to crack our code. So we kind of live in a golden age of cryptography. Theoretically, our code could be broken, but realistically, the complexity of the code makes it unbreakable. But that hasn't stopped people trying to get truly unbreakable codes, and that's where quantum cryptography comes in. And the idea with quantum cryptography, let me try and break this down. Stage one is, okay, there is an unbreakable code already. It's called a one-time pad. It's just a random series of letters, a random series of numbers. If I kind of mix that randomness in with my message, because I'm adding randomness to the message, the result will be random. And if something's truly random, nobody will ever be able to decode it. The only way they can decode it is if they take my random, what's called a one-time pad, add it again, and then the message will reappear. So that really exists. The one-time pad. If I get my one-time pad to you, Robin, you can read my messages, and no one else in the world will ever have any hope of reading my messages. The problem, however, is how do I get my one-time pad to you? Okay, I can't put it in the post. I can't encrypt it because somebody might break that code and get the one-time pad. How do I get a one-time pad to you? And the way I'm going to do this is by sending it via photons. And I'm going to send you a series of photons that are polarized. I think if it's vertically polarized, I'm going to call that a 1. And if it's diagonally polarized, I'm going to call that a 0. I think let's call that 1 and 0. 1 and 0. And I'm going to send you these photons. And that's my one-time pad. Now, the one thing I'm concerned about is that somebody might be eavesdropping on our optical fiber, and they may be listening in and copying down the photons as they come through to you. But we can kind of check if anybody is eavesdropping, because one of the things about quantum physics is if you observe something, you will change it. And the eavesdropper will change what I'm sending if they try and eavesdrop on it. And so, for example, one way we can do that is if I send you a photon that's vertical and the eavesdropper tries to measure it diagonally, there's a 50% chance they will measure it diagonally. Now, if you measure it horizontally, there's a 50% chance that you'll measure it because you're not perpendicular to it. You might still catch that photon. So you, with a horizontal polarizer, with a horizontal filter, you've caught what was originally a vertically polarized photon, which should never happen, except our eavesdropper was in the middle messing around. And so we can use this to see if the eavesdropper is there. If the eavesdropper is there, we throw away the one-time pad. If the eavesdropper is not there, then we know we've got a legitimate, truly random one-time pad that we can use for our communication. And that system, which is truly, I'll come back to that in a second, but let's say it's truly unbreakable, is now commercially available. There are people at the university in Geneva and other companies have set up quantum cryptographic systems that are being sold and being used by banks, presumably in Geneva. It's theoretically unbreakable, but one of the things in cryptography is that you have to implement it. You have to build a system. You have to build these polarized filters. You have to build photon generators. You have to build optic fibers. And if Eve can somehow muck around with the technology and infiltrate the technology, then the system can be compromised. But so far, quantum cryptography seems like the ultimately unbreakable code. It's kind of reassuring to have that in the background, because although the codes we have now are unbreakable, theoretically unbreakable, if they were to be broken, you completely disrupt the balance you disrupt the balance of the world. So suddenly superpowers that are fronting off against each other can steal information and maybe exploit vulnerabilities. The whole e-commerce world collapses because we can't have secure financial transactions. So the breaking of the current codes would be a complete meltdown of society. But quantum cryptography might be there in the background to help out.
Right, which has now meant that quantum coin flipping is all sorted, and we'll come back to you before the end of the show. Otherwise, you might require some addenda there. Question for Monica, who's back with us again. So many different angles that we've had today. This is, we haven't got a name with this one, but do you get annoyed when the media grab bits of quotes and inflate those to run major misleading headlines with your science? I'm thinking about how earlier this year there were lots of headlines about you saying there might be octopus creatures on the moons of Jupiter, and that's not really what you were saying at all.
Crikey. Yeah, I do get annoyed about this sort of thing. I don't blame journalists. I don't blame you, because they need head-grabbing titles. Otherwise, people aren't going to read the things. But it is nice to be quoted accurately. I can't remember saying anything about octopuses on the moon. Blimey. But I'm fairly certain there aren't any, if that clears up that mystery.
What we've just found out is the new scientists have been hacking your phone, so we'll.
Fine, that's okay.
But is it? What do you think the way is? Because it's something we've talked about with Helen before as well, and quite a few people. That way of somehow making sure that the full scientific idea gets it, not just that one bit from the paper, not just that bit that's in the kind of in the press release. Is there any way of at least trying to curb that, or will you always be at the mercy of that kind of
You'll always be at the mercy of that kind of journalist, because the soundbite is what is required. Even if the journalist interviews you for an hour and transcribes faithfully every word you say, when it gets to the final programme or the final article, it's going to be edited down to, Monica Grady said, that's really interesting. And no matter what else you've said. Now, there are places where scientists, where academics can write things and then get them edited by journalists so that it actually sounds reasonable. And that's a blog site called The Conversation, which is a really interesting thing to look at. But again, it's still, if you want to grab the headlines, you've got to be in some ways, if you want to get a scientific message across, you've got to be prepared in some ways not to sacrifice your scientific integrity, never that, but to be able to talk in a way that can be chunked so that you say something sensible in 5 words rather than 5 paragraphs. I'm not good at that because I just talk far too much anyway.
There's I'm sure we probably mentioned this on before, but there's the lovely phrase Gell-Mann amnesia, named after Murray Gell-Mann, who said that whenever he would read something about anything that was any close to kind of his work in physics in a newspaper, he'd go, this is all nonsense. This isn't anything that we're working on at all. And then he would turn the page of the newspaper and believe everything else in the newspaper and go, well, hang on a minute. Why is everything else going to be right? It's just going to be my area of expertise that's wrong. I think that's a very, and I would say to everyone watching this, when you, I'm sure most of you know, aware of this, but next time, when you see a really good and interesting story in a newspaper about anything going on with scientific research, do go. The Conversation is a very good idea to go somewhere like that. There are many places you can go. Try and find a site where there's experts writing on that in a lengthier way, which will then cover some of those ideas. While we've got you, Monica, just in case, I'm just going to stay with you for the time being. This is from Frankie. Frankie says, I read an interview with Monica last week. Let's hope it might be about the octopus again. Let's just find out. Right. I read an interview with Monica last week where she said Mars has a long history of mission failures. Is there something specifically difficult about missions to Mars beyond the standard caveat of space is hard?
Right, Frankie. Well, yes, I did say that. And there isn't anything that's particularly special about Mars. Space is hard. There are a lot of there's been a high percentage of mission failures, but that's because most of the first ones just failed because the technology wasn't there. Over the last few years, we've had a much better, I was going to say hit rate, but that's probably completely not the right phrase to use. We've had a good success rate. There are things that are difficult, though. Mars has an atmosphere, so whenever a lander has to come down through the atmosphere, it has a chance of getting hotter and hotter and hotter and burning up. Things like the Schiaparelli lander, something went wrong with that, with one of the, I think it was one of the detectors, and it didn't detect how close it was to land before it actually landed. And so there's all sorts of odd technology things that go wrong, but by and large, fingers crossed, because we've got a couple more going this summer, by and large, fingers crossed, things are getting a lot better.
I do think there is also the speed in which we get non-experts criticising. I remember Colin Pillinger, getting loads of things, and you go, it got to Mars. There's a lot of people who've got lost on the way to Norwich. This has got to Mars. And there are, as you said, making sure you're dealing with all the variables. I think that is, it's a tricky thing. This is this one's for Helen. Well, it's not necessarily. In fact, everyone can have a go. It's only just about explaining gravity. You'll all be fine on that. This is from Charlotte, who says, "I don't understand gravity at all. Why does it make things fall and not float, attract but not repel? Does it have to be this way?" Helen, how do you feel about going with the gravity question today?
So gravity is different from the other the three. There are four major forces in physics, and gravity is different from the other three because it's only attractive. And the model for this is that it's a different. So one of the problems in physics in general is that gravity and quantum physics are not reconciled. And so in the quantum world, we have a model for how forces are transferred and what they do. And it's to do with little entities moving between things and exchanging, not quite particles, but they are particles, but exchanging little things. Whereas gravity, we explain using general relativity, which is where we say that mass affects the space-time around it. And so actually the general relativistic explanation for gravity is that actually things are going in a straight line. It's just that space is curved because of there being a lump there. So the reason gravity is different, and it can't be one way of saying the reason it's different is that our model for understanding gravity is completely different to our model for understanding the other fundamental forces. And we, at the moment, we can't reconcile those two things. There is hope that studying things like black holes, where they sort of have to join up around the back, somewhere in a black hole, general relativity and quantum theory have to get on somewhere. They do exist in the same universe. So there was a lot in the question, and I can't remember all of it. But one of the reasons that we can't give a simple explanation of why it's different is because we haven't got, fundamentally, in a really fundamental way, we haven't got a good model for why it's different. It just acts. Our model for understanding it is completely separate to our model for understanding the other forces.
Isn't there also a kind of a gravity that repels as well that you will find in? Is that right? That there's I'm sure I was reading in Katie Mack's book that there was there is a point where you would then get what might be repellent gravity.
If Katie Mack said it, it's probably correct, but it's not something I'm familiar with.
Think of is that we have this for when I was a student, the assumption was that the universe was expanding, but it was slowing down because all the mass in the universe should be pulling it back. It might still be moving apart, but it would be slowing down. And maybe it was going to come to a halt, and maybe there might be this big crunch with the gravity pulling the universe back into itself. And then in the 90s, when they sent up some satellites to measure how much was the universe slowing down, turned out the universe is speeding up. So there is some kind of anti-gravity force, and they call it dark energy. People may have heard of dark matter, and they may now have heard of dark energy. Dark energy seems to be this driving force that's causing the universe to accelerate away into oblivion. And that adds to the mystery. That really does add to the mystery of maybe gravity is like it is around here on a localized way. It behaves in a certain way, but over vast distances it maybe repels. That's a weird thing. One of the other weird things about gravity is it's incredibly weak. We think gravity is very strong because it pulls us down onto the earth, and we take huge rockets to get off the earth. But if you take a tiny fridge magnet and stick it onto your fridge, that magnet, the force of magnetism or electromagnetism or whatever it is, can defy the entire gravitational pull of the whole Earth on that magnet and not fall down. So it is a weird one, and we, as Helen says, we have an understanding of how gravity works, but it doesn't fit in with anything else we understand about the other forces. So there's a huge amount of work still to be done.
The dark energy bit always reminds me of that. I think it was a New Yorker cartoon where you see a big blackboard and it's got two sides of an equation. Then in the middle, it just says, and then the magic happens. And he goes, yeah, I think we still need to do a little bit more work on this.
But it's interesting because actually the dark energy thing, that it's been written in photographs from telescopes like the Hubble telescope for decades, and I don't think they really took it seriously. They saw that if you looked at the way things were spinning and the way that things were moving, it didn't match the amount of gravity that you could justify from the planets and the black holes and the other things. It was written there. Monica probably knows more about this, right?
Well, I was going to say that's the dark matter rather than the dark energy.
Dark energy. Okay, that's my mistake.
It's the dark matter which controls the motion of galaxies and things. But it's the dark energy which they say is the energy in the vacuum. It's like, right, okay, that vacuum's empty. How can it have any energy in it? And this is, again, where the magic happens. But the other really mysterious thing about gravity is that it happens instantly. And it happens, we haven't got that, okay, we have the acceleration due to gravity of some things falling from a big height. But it's like we don't know how there is the transfer of the pull of gravity. We don't understand that. And it is really mysterious. So whoever the caller was, it's like fair play to them.
Looking back, is there perhaps a regret that the titling of dark matter and dark energy, because it does lead to a lot of confusion, I think. We've done discussions before on Monkey Cage and various live events as well, that it's like, oh, well, they must be directly connected then. That's because they're the same thing. Looking back, could we have done more work when it came to kind of the naming? Should we get someone maybe from the advertising industry in to look some... No, you're entirely correct, Helen.
Here's my problem with naming, actually, is that once you give it a name, everyone assumes you know what it is.
Yeah.
And actually, there is an argument, I think, for they sort of need to be names in brackets, because they only call it dark energy because the word for it is actually the name of the gap. It's in the knowledge. It's not the name of the thing in the gap that's going to fill the gap. It's just the name of the hole that someone has to fill at some point.
And the confusing thing about calling it dark matter and dark energy, I mean, we all know that energy is matter times the square of the velocity of light, but not dark energy and not dark matter. They're not connected like that at all. But it sort of really draws you along that path.
Simon, we as we're talking about some of these kind of cutting edge worlds, Virginia has says science writers often joke about how their book is out of date with new research before it's even published. Has there been, actually they very rarely joke about that until it's at least been out for a year, because otherwise they're really damaging sales, but I know what you mean, Virginia. Has there been any new discoveries in the last 15 years that would have changed anything you wrote about in your book Big Bang, or are we still pretty much in agreement on all of that?
I've always been quite cautious. Big Bang is not about our current understanding of cosmology. The Big Bang is really about how did we get to where we are today. So what did we used to think that where did we think the universe came from in the 19th century? Who were the people that came up with the idea of a Big Bang? What was the evidence that supported them? What were the controversies in the 40s and the 50s and the 60s that led to this kind of battle between those who thought the universe had been here forever and those who thought it had been created, and how was that eventually resolved in the mid-60s and into the 70s and increasing evidence in the 80s. So my book kind of stops in about 1990, and that's sort of deliberate because I just didn't want to get into all the controversies that are happening now, which, so when my book was published, I don't know if dark energy was a thing or not, but as you say, it would immediately be out of date. So things like, Fermat's last theorem, that book ends when Fermat's last theorem was proved. There's nothing else that's going to make that book out of date. The code book, that book is now 20 years old, and a lot's happened in information security in the last 20 years. But my book is not really a modern, a look at modern cryptography. It's really looking at the evolution and the history of it. So I try to kind of protect my books from going out of date, and hopefully, homeopathy still doesn't work. But interestingly, but Edzard and I did review all the topics in our book when we brought the paper book out, and I think it was the Alexander technique, which we'd given quite a hard. We'd been very negative about the Alexander technique, but a study had come in. It was a respectable study. It probably built on something else that had been published, and so we changed our comments about Alexander technique based on that. So when you get new evidence, you change your opinions, and that's what we did. But there wasn't a huge amount of change between the hardback and the paperback.
So I got worried there because I thought just before the end you would suddenly burst into singing a David Hasselhoff song, and we'll go, that's the Berlin Wall's kicked in now, hasn't it? It's an absolute disaster. This is a question for Monica from Gemma. Gemma says there's so much coverage and excitement about the Philae landing, and then we, at last, in the major news, we didn't really get to hear anything else about what science came out of the mission. So I guess my question is, what have we learned since?
Oh, well, we've learned all sorts of stuff. I mean, we've learned the composition of the ice of the comet. We've learned what it was made from inside, whether it was lots of sort of small pebbles. We've learned more about the actual building blocks, the different types of organic compounds that were there. We've learned about the rate at which the ice and the other volatiles come off the comet. We've learned a whole load of stuff which really helps us understand a lot better about how comets are made, about what they're made from, and why they were made where they were, and what other bits and pieces have gone into making them. We've learned a lot about the way they move, the way they spin, the way they're formed, in terms of are they bits that have crashed into each other, the relationship with other bodies in the solar system. So there's a whole load of stuff that we've learned. Unfortunately, we didn't learn anything like, hey, yes, there actually is DNA on this comet, or anything like that. So the headlines for us have been, it's been another fantastic step forward in understanding the origin of the solar system and understanding the building blocks of life, but nothing which is going to say we found life on a comet, or we can explain viruses coming from outer space, or anything like that. All we can say is that side of stuff is nonsense.
So in terms of what might have been predicted in terms of the results you got, what has been the one which perhaps was most, if anything, counter-instinctual, or the biggest leap in terms of what you had presumed and what actually?
Well, I think the biggest leap came the day we saw its shape. And it was that funny sort of duck-shaped thing, which was completely not expected. Totally and utterly not expected. The next thing that we found that was unexpected was that there was so little ice on the surface, that so much of the surface was black. There had been an understanding or a thought that so much of that material will be stripped away each time the comet came close to the sun, and that it wouldn't get a chance to build up. But the fact that there was so little ice compared to the refractory, the hard nature of the black stuff, that was a real surprise as well. So it's like you start off with a model that comets are dirty snowballs, so they're ice with a bit of dirt mixed in. You then modify the model to say, well, they're not dirty snowballs, they're icy dirt balls. And now we've got something, well, actually it's a dirt ball with a hard crust and a bit of ice. So it's been, the evolution of the models has changed quite a lot.
Every single one of those answers sounded like it was the first day at the biscuit factory when they were researching a new marshmallow-based treat. So we're with the final questions now, for just one for each of you. And thank you very much, by the way, everyone, for watching. And thank you very much, Monica, for your tenacity, which, of course, is one of those things that you need when you work in the area you do. But what we found out, just sitting literally on the router is the way that manages to work. So now this is about the series that you've just been doing on Cosmic Shambles at the moment, Helen, which is in one of the episodes of the Easter series. Helen says she didn't feel terrified about being on a parabolic flight till she looked out of the window. I'm wondering if it was just purely mental terror when she looked out the window, or did she actually start to feel physically sick too once the reality came into focus?
So it has been a repeating trend that everyone is disappointed that I did not feel sick at any point, I did not vomit, and I did not get seasick. And this remains true when I was looking out of the window. Everyone has been desperate. They're like, but you must have been sick. And I'm like, no, I was perfectly fine. Really, perfectly fine. But what was interesting, so for those who didn't see that part of the series, on the parabolic flight, in the main, so there's two bits of the plane. They kind of cut off the front third. They black out the windows. That's the experiment area. The back third of the plane is still the normal seats in the windows. So when you're in the experiment bit, you can't see what's going on. Gravity changes a bit. Totally fine. In the other bit, you can see what the plane is doing. You can watch it falling out of the sky. And so it's only the last parabola where I went to the back. And so I didn't feel at all sick. But I did viscerally understand what the plane was doing in a way that I had obviously logically understood before, but my body went, oh, that's what's going on. And because the thing that I didn't expect was that you can't feel at all that the plane is tilting. When you're in the main body of the plane, it just feels like gravity increases and then it decreases and then it increases again. You've got no idea that you're actually standing on a surface which is at 45 degrees to the horizontal. So no, I didn't feel sick, but I did have to struggle not to swear. Like, you know, and I've done a lot of odd things in my life. I've been very privileged to be chucked out of planes and dropped down things and all that kind of stuff. And so there's a logical thing that you are safe because you have done this 29 times before. It's not going to kill you on the 30th time, but you feel it because your body's got all that extra sensory stream of what's actually going on. And it is a very different experience. But no, wasn't sick. Sorry.
That's one of the things. It's just not enough in the movies about space exploration, because, you know, apart from Apollo 8, which, you know, famously, of course, had terrible attack of diarrhea and all manner of other things as well. The bomb, But sometimes I've done shows with astronauts, and someone said, "Oh, don't ask that because he was very famous for throwing up." So there's loads, but that's somehow ruins the pristine image. Unless it's really dramatic, we keep a lot of that quite quiet, don't we? Some of the more
it's interesting because obviously I spend a lot of time at sea. I study big storms. I am in 10-meter waves. That's what we go there for. And it is people are always asking, aren't you seasick? And no, the answer is no there as well. And most oceanographers aren't. I do know some people who are, but most of them aren't. And it is just, you go into that is your working environment and you get used to it, but no one wants to hear that you've got used to it. And I think there's a relatability thing. Every time I say, no, of course I wasn't sick, I feel that people get a bit more distant from me because they think they would be sick and they sort of want to think that's how I would feel. And it's very hard to say to someone, it's not like that. That thing that you think is absolutely what it's like. It's not like that. But they're so, it makes it very unrelatable. So I do worry about saying it, but it's really important to say it's not true. And also humans, seasickness medication, people have put a lot of work into that. So if you do get seasick, there are ways of dealing with it.
Simon, I'm going to ask you two things. One question, I don't know if it actually came from you or not, is are you working on a new book? And if not, what's something you'd like to really dig into? And on top of that person's question, I'd also can you tell us a little bit about parallel.org.uk, the kind of puzzles, if you can give us maybe an example of the kind of thing that the 15-year-olds are up against?
So the two things are kind of related. I'm not writing a book. I've kind of given up. I kind of think I've written a few books and I kind of just worried about putting 3-4 years of work into a new book, which maybe nobody will want to read, and kind of think if I've got 3 or 4 years ahead of me to do something, what would I really love to do? And the thing I really love to do, the thing I'm really passionate about at the moment, is thinking how, if you're good at maths at school, how do you get to be really good? Yeah, I think schools do a great job of helping kids who are struggling, and schools do a good job of helping kids who are in the middle become good. But if you're good at maths, I'm not sure our schools are designed to help you become great at maths. And so Parallel is part of that. Parallel is a weekly smorgasbord of puzzles, riddles, maths problems, number file videos, all of that good stuff. And there's one for year 7, one for year 8, one for year 9, one for year 10, one for, we haven't got 11 yet. We will do next year. And we've had about 300,000 completed. So wow. Kids who do it, come back week after week. And that's the thing. If you're going to do it every single week and broaden your horizons and stretch your brain a bit. So that's one element of what I'm trying to do. I'm in parallel to Parallel. Thinking about what can schools do, or what can we directly do with schools to help them stretch ththose kids who are good but could be great, so that more people have access to being excellent. That's the fundamental thing. If you're a young girl who's 11 or 12 and you come out of primary school bouncing with enthusiasm for maths, how do we develop you into a further mathematician at A level and then a computer scientist as a degree or something? So So I've got a really interesting project which I'm going to start in the autumn. But if people follow me on Twitter at SLSingh, SLSingh. I'll be talking about that. But yeah, no, I think we're doing some really interesting things. I'm really excited about that in such a way that I don't want to write books or do anything else at the moment.
And also, your last book was The Simpsons of Mathematics, which was, I mean, you'd almost finished writing that book when you then threw away the whole thing and started again, didn't you? You suddenly went, I've got the wrong angle. I mean, and that's an incredible thing to have to do.
Yeah, it's so I'd written that book. All of my books have sort of 6 or 7 big chapters, and that's the way I write books, and that's where I thought I'd write this book. I had a big chapter about pi, which crops up in various places. I had a big chapter about Lisa. And then I was flying over to meet the writers. I flew over to Los Angeles to meet all of these writers and spend a week with them. And literally in that 9-10 hour flight to LA, I restructured the entire book. So instead of having 6 big chapters, it had about 18 little chapters, which was much more appropriate. It was much more fun, lighthearted, much pacier, much more in keeping with what The Simpsons are all about, and Futurama as well. And that was a really great flight. I remember the idea of the Big Bang came from, I was on a flight going to America, and the person next to me, I told them I was a science writer, and they were talking to me about science, and they said, well, tell me about the Big Bang. And I thought, well, this is incredible. We have this amazing theory of the universe and where it came from. And yet somebody here who's educated had no idea what the Big Bang theory really was. And so I wrote the proposal for Big Bang on the flight, faxed it back to the UK, because those were the days when we had faxes. And within the week, that was it. We had the book deal, and I was ready to start writing it. So playing seemed to be quite a fruitful place for me to do work, it seems.
Well, I can see why you're not writing at the moment. The lack of transience means it's quite impossible for you to create anything.
Exactly.
The final question for you, Monica, is from Paul, who says, if you could feel a piece of rock from anything that exists within our solar system, what would you like to get hold of?
Ooh, wow, what a difficult question. What would I like to get hold of? Oh, gosh. I think I'd like to get hold of a piece of the ocean floor of Europa. All right, because we know Europa's covered in ice, and we're fairly certain there's a lake, a sea below it, an ocean below it, and then there must be a surface underneath that ocean, but we don't know what that's made of, and we don't know how the ice has changed it, and we don't know if there's any creatures down there. We don't know whether there are any hydrothermal vents producing fantastic copper minerals like malachite and stuff like that. So wouldn't it be fantastic to get a chunk of malachite from the ocean floor of Europa? That would be really cool. And I think that will please Helen as well.
Yeah.
I'm in. As long as it's brightly coloured, I'm in.
You've invented green. Congratulations. Thank you very much, everyone, for joining us, to Monica, Helen and Simon. And we'll be back at the same time next week. I just mentioned again, of course, that you can still watch Helen's show on the BBC, which was Ocean Autopsy. That's on iPlayer now. And also keep up to date with the Cosmic Shambles series she did with Ginny Smith as well on Easter and the Parabolic Flights. And you can see the suspense of whether she's going to vomit or not, all of these different things. Spoiler alert, we've kind of found out she doesn't, but nevertheless you can still get some of those kind of sensations. Simon, we've mentioned again, parallel.org.uk. Keep up to date, find out if you've any kids who are really into maths, if you've got friends whose kids, this is, steer them in this direction. I know how much Simon loves enthusing people about mathematics, and it's a wonderful thing. Monica's work will continue to if not take us to Mars, at least bring some things back from Mars one way or the other. We'll get hold of something. Thursday night, 8:00. I'm a Joke and So Are You. That's on our next, one of our next live shows, and that's going to be with Josh Cohen as well, talking about various different ideas of therapy and anxiety. Go to Cosmic Shambles site to find out about all of these things. And that's it. The tip jar's at the bottom if you fancy putting something in there, and if not, that's fine as well. Or you can also join us on Patreon. This is how we fund. We're doing about 5 shows at least a week, and Patreon means that we can keep making them. So thanks very much, everyone. See you next Sunday for another Sunday Science Q&A.